All right, welcome to another module. This module is on chemical reactions. Uh, we're going to first talk about how to balance chemical reactions and then delve into the different kinds of chemical reactions and how to categorize them and how to identify the different kinds or types. So the first thing we're going to talk about, of course, in this video is balancing chemical reactions. Now, the reason we balance chemical equations is because we would like to follow the law of the conservation of matter. We talked about in the very first chapter that the law of the conservation of matter means that if you go into a reaction or a chemical reaction with, let's say, 4 hydrogens, when you come out of the reaction at the end, even though the atoms may be rearranged, they need to also have 4 hydrogens total in the products. So let's look at how we might describe or make sure that the reaction itself is balanced and that the law of the conservation of matter is conserved. So the first bullet point says that the chemical equation describes chemical reactions and how atoms move around and rearrange to form new substances. Think of it like a recipe with ingredients called reactants on the left, separated by an arrow, and the products are on the right. So they do want to make a point that you want to make a note that all of these are the reactants here, and all of these are the products, right? The ones before the arrow are the reactants, and the ones at the end are the products. There's also a thing that says that we like to represent the states of matter. Remember, the states of matter are solid, liquid, and gas. And so we would like to represent them in terms of the substances that we either add as reactants or form as products. So here you've got the states. You've got solid for S, L for liquid, G for gas. And aqueous means that that substance is dissolved in water. So for example, if I have NaCl aqueous, that means that my NaCl or table salt is dissolved in water. So that just basically means I've taken some salt and I've dissolved it in water, and water is a solvent that basically allows me to do the reaction in a liquid form. So what are the whole numbers shown in red? Let me just erase my highlight so you can see the red. The numbers in red, and these are very important, these ones here, okay, must balance the equation to maintain the number of atoms on both sides. So if you look at it, if I wrote the equation like this, H2 gas is reacting with O2 gas and it's forming H2O, this would be an unbalanced version of the reaction. H2, the little subscript 2, means that H and H are connected together. O2 means that O and O are connected together. And from Lewis dot structures chapter, we know O2 is a double bond. And then it forms H2O. Now, if you look at what we've drawn so far, you'll see that the reaction is not balanced, right? Because you've got 2 oxygens on the left and an oxygen on the right. So it can't, this is not possible. It breaks the law of the conservation of matter. That's why you need the 2 in front, because the 2H means that now there are 2 molecules of H. And then 2H2O means that there are 2 molecules of H2O being formed, right? So that's what that 2 means. 2 means that there are 2 separate substances or molecules, and then these things are reacting together and forming 2 of the waters. So that now if you count, everything is balanced. You have your 4 hydrogens. Yes, they're rearranged and connected differently now. That's the hallmark of a chemical reaction. And you've got your oxygens, 2 oxygens. Again, they are rearranged and no longer connected to one another. They're connected to the hydrogens now in water. But again, the number of oxygens and the number of hydrogens are the same. So when we balance, what we're doing is we're just taking a number, putting it in front, and making it balanced so that the law of the conservation of matter is applied. Okay. So this video basically will help us to write the correct numbers in front. So these numbers in front, how do we know what numbers to write in front? That's what this video is all about. All right. So now that we understand in terms of why we are trying to balance equations, let's actually balance some equations. Now, if you've done balancing equations before and you feel like you have a good handle on it, you can actually pause the video and write down these equations on a clean sheet of paper and try and balance them and see how you do. Okay, if you've never balanced equations before, it might be good to watch me do it first, then go back, rewrite this on a clean sheet of paper and do it again, and then check your answers. Really, with chemistry, practice makes perfect. So again, you don't want to just watch me do it. You want to also do it yourself. All right, so under balancing chemical equations, we want one, same number of atoms to appear on both sides of the equation, same number of atoms. That's what we discussed in the previous slide. The chemical formulas cannot be altered, i.e. don't change the subscripts, okay? Again, if you're thinking about, H2 plus O2, this was your unbalanced equation, right? It forms water, right? Some students will say, well, Dr. Chang, why don't I just put a 2 here and now it's balanced, right? But the problem here is that H2O2 is not what we think it is. H2O2 is this. This is hydrogen peroxide. And if we've used any kind of hydrogen peroxide before, we know that that is not something that is drinkable. It is not the same as water. It has very different chemical properties than water. And so you cannot just write a 2 right here and just say, oh, it's balanced. Because the moment you change the subscript, you change the formula. And the moment you change the formula, you change the identity of the substance. So if you change the formula, because you change the subscript, the substance is no longer the same. And the problem with that is now it's no longer the same expression of a chemical reaction. So whatever you do, do not change the subscript numbers. When you're balancing, you can only change the numbers in front. We will talk in one of the next videos about when it is okay to alter the subscript numbers. But for now, when you're balancing, you cannot alter the subscript numbers. Other reactants or products cannot be added, so you can't just add another O2, right, at the end, and balance with the smallest whole number of coefficients. So the numbers in front, they have to be the lowest whole number of coefficients, or the smallest whole number of coefficients. And we'll talk about that in a little bit as to what we mean by that. All right, so I went ahead and copied the first equation onto a clean sheet of paper. And so I'm going to describe what I'm doing as I do it. So the first step is I'm going to tally the atoms or ions, okay, under the arrow. So underneath the arrow, where clearly is the differentiating mark between the products and the reactants, I'm going to write K, Cl, and O. I've basically tallied or listed all of the atoms in the reactants and products, okay? Now I'm going to count. I've got 1 potassium, 1 chlorine, and 3 oxygens. 3 because of that subscript 3. On the other side of the equation, I have 1 potassium, 1 chlorine, and 2 oxygens, okay? So given that this is the case, we can see that the oxygens are not balanced. And remember, I can't change the subscript, so really I have to write numbers in front of the oxygen and the KClO3 to be able to balance it. So between 3 and 2, the lowest common multiple is 6. So what I want to do is I want to write a 2 in front so that this 2 times the 3 becomes a 6. So now I've got 6 oxygens, right? I also want to write a 3 in front because the 3 times the 2 makes this a 6. Okay. Don't forget, though, that writing a 2 in front of the KClO3 also changes the amount of K and the amount of Cl. Remember, the K is really 1, Cl is also really 1, we just don't write it, right? So the 2 times 1 makes this K a 2 and makes the chlorine a 2 as well, right? So really, it is important to recognize that when you write a number in front, like this affects this one, the potassium, the chlorine, and the oxygen count across the board, okay? Now, because I've balanced my oxygens, my K and my Cl are not balanced, so I'm going to put a 2 in front of the KCl so that my potassium is 2 on the right side and my Cl is also 2 on the right side. Now, the reaction is balanced, 2, 2, and 6. So this is the balanced reaction. So 1, I've put a tally of the atoms underneath. Then 2, I balance using the numbers in front. Okay. I often will start with the most complex compound. That's why I started with the KClO3, because that is the most complex. It is ternary, right? Another way of saying this is ternary. Okay, and then the last step is if you have O2, right, or H2, or anything diatomic, right? Remember, diatomic is like H2, O2, Br2, etc. You can write any number in front. To get the number you need. And we'll talk a little bit more about rule number 3 in a later problem to just show you how that works. Okay, but really, we're gonna just again do the rule 1 and 2, and then I'll show you how to do 3 when it pops up. You don't always need to do that, but sometimes you will need to apply that rule. All right, so again, I'm gonna copy and paste my rules. Okay. Paste it right here. So the first thing I should do is tally, right? So underneath the arrow, I'm going to write H. Okay. I'm going to write, now notice I'm going to write NO3 because that is my polyatomic ion. And I can do that because NO3 is also here. You see? So because the polyatomic appears on the left and the right, I can count the entire polyatomic rather than breaking it up into nitrogen and oxygen. All right, Ca and C and O. Now you might be like, well, why don't you write CO3 because CO3 is carbonate and also a polyatomic? It is because CO3, the polyatomic, does not appear on the right-hand side. So you've got to separate them since they don't appear on the right-hand side. All right, so now that I've listed everything out underneath, both as atoms and ions, I'm going to tally and count. So I've got 1 hydrogen, 1 NO3 polyatomic, 1 Ca, 1 carbon, and 3 oxygens. Then I have 1 carbon, I have 2 hydrogens, I have 1 Ca, and I have 2 NO3s. Now with the oxygen, be careful. I'm not going to count this oxygen because this oxygen is already accounted for in the NO3. But I am going to count these oxygens here. And instead of writing oxygen is 3, it is 3, I'm going to write 2 plus 1. The reason for that is if I put a number here, 3 in front, for example, It does not change the entire number. And if I wrote 3, oftentimes students will say 3 times 3 and write 9. And that would be incorrect because 3 only affects this 2. So it really is 6 plus 1. So it ends up being 7, not 9. So really, you don't want to write the number together if the number is separated. Okay? All right. So now let's go ahead. And again, we want to start with balancing the most complex molecule. So in my mind, it's the calcium nitrate, okay? So really, I have 2 NO3s, and I'm going to write a 2 here to make it, I want 2 on this side as well, right? So I'm going to make that a red. So this makes it 2 NO3s and makes the hydrogen 2 as well, okay? Now, if you look at it, everything else seems balanced, right? The calcium is balanced. Carbon is balanced, 2 plus 1 is 3, so everything else is balanced. So in this particular case, just by writing that 2 in front of the HNO3, this reaction is balanced. Hopefully, it would be nice if every reaction was this easily balanced. You'll see that it is not the case, but oftentimes reactions are very straightforward to balance. All right, looking at the next one, again, we're going to tally underneath, and we're going to go carbon. Oops. Doing the same color. Carbon, hydrogen, and oxygen. It's very straightforward to tally this one. Okay, I've got 8 carbons, 18 hydrogens, and 2 oxygens. 1 carbon, be careful, 2 hydrogens, and 2 and 1, so 2 plus 1. Okay, so now that we have that all listed out, step number 2 is to balance with the numbers in front. Again, we want to try and go with the most complex. In my mind, this is the most complex because that has 8 and 18, a lot of atoms, right? So I'm going to go ahead and write 8 in front of the CO2. And the reason for that is because if I write 8 in front of the CO2, that fixes the carbon count. I get 8. Now this 8 affects this oxygen count, so 8 times 2 is 16. It does not affect the other oxygen count. Now we're going to go ahead and look at hydrogen. Hydrogen is 18. I obviously need to multiply this by 9 because 9 times 2 is 18. So this gets me 18 hydrogens, but it also affects this oxygen, which is now 9. Okay, so if you are counting along with me, 16 plus 9 is 25. So my carbon count and my hydrogen count look good, but my oxygen count is not quite right. So really, if I have a 25 here, this would fix the issue altogether, right? So really, you might say, okay, well, what number can I write in front of oxygen to make it 25? If I write, there is really no whole number that I can write, okay? But here, if you look at rule number 3, if you have O2 or H2, anything diatomic, any X in front to get to the number you need, right? So I can write here, I'm going to write O2 here, okay? I can write 25 over 2, okay? So X over 2, right? So basically, if I want 25, I just put it over 2. Because if you think about it, 25 over 2 times 2 is 25, right? So if I put a 25 over 2 here, now I have 25 underneath, okay? That looks pretty good. Now everything is balanced. And this is the case for all diatomic molecules. Like, for example, if you have H2 and you need, let's pretend you need, 35 H2s, then you can write 35 over 2 in front. And again, 35 over 2 times 2 gets you 35. Then you have 35 hydrogens. So whatever number you need, put it over 2. Remember, you can write any number you want in front of the diatomic, as long as it gets you the number you need. In this case, what number you need over 2 gets you what you need. All right, now you can't leave it as 25 over 2 because one of the rules says that you need to have whole number coefficients, right? Whole number means 1, 2, 3, 4, 5, 6, 7, 8, because Atoms really don't exist as half atoms, right? But you can fix that really easily. All you need to do now, once you've used the 25 over 2 as your get out of jail free card, is multiply by 2, right? That will get rid of the denominator altogether. So then you end up with 2C8H18. 25 over 2 times 2 is just 25. O2. Now you've gotten rid of that fraction. 8 times 2 is 16 CO2, and 9 times 2 is 18 H2O. Okay? And again, if you want to check underneath and make sure your tally is still correct, you can. Okay? So you just think 2 times 8 is 16. 2 times 18, that's a harder one. You might need to pull out a calculator for that. It is 36. 25 times 2 is 50 oxygens. 16 carbons. I'm going to count the oxygen last. 18 times 2 is again 36 hydrogens. Now for the oxygen count, 16 times 2 is 32. And 18 times 1 is just 18. And 32 plus 18 is 50. So again, we have balanced the equation. So some of the equations are a little bit more tedious to balance. That's okay. I really like this problem because it actually allows us to use this rule number 3, which I think is very useful. All right, let's look at the next one, the last problem. We have carbon, hydrogen, nitrogen, and oxygen. Carbon is 3, hydrogen is 5, nitrogen is 3, and oxygen is 9. Nitrogen is 2, hydrogen is 2, oxygen is, be careful, this is 1, this is 2, and this is 2. So 1 plus 2 plus 2. And my carbon count is, of course, 1. All right. Again, you want to start with the most complex. To me, this is the most complex. So let's go ahead and fix the carbon, hydrogen, and nitrogen count. We have this diatomic oxygen as our get out of jail free card because we can put whatever number we want in front and it'll fix the situation. However, I would like to say this. We already know that this N3 is difficult to fix, right? Because then I'm going to end up with a 3 over 2 in front of this number. I think the easiest thing to do is if you see an odd number like that, you can actually just know you need to multiply by 2, at least 2, to make it even, right? So I'm going to go ahead and do that first. I'm going to go ahead and multiply by 2 and get 6, 10, 6, and 18. That will make balancing the nitrogen a lot easier. All right, so now that we're here, let's go ahead and balance the carbon first. The carbon, we need 6, so we need to put a 6 here. This affects this oxygen count. 6 times 2 is 12. Okay, then let's fix the hydrogen count. We need 10, so we're going to put a 5 here. This affects this oxygen count, which now is a 5. Okay, and let's fix the nitrogen. We put a 3 in front. That makes it a 6. Okay, easy enough to do. So really now the oxygen is the only thing that's problematic. We have 5 plus 12, which is 17 plus 2, which is 19. If only this was a 1. If this was a 1, then I would have 18, right? So really, I just want this to be a 1. So we know how to do that, right? Because the rule number 3 says I just put whatever number I need over 2, right? If I need 35, I put 35 over 2. If I need 25, I put 25 over 2. If I need 1, I just put 1 over 2, right? Because 1/2 times 2 is 1, okay? So now I'm good because 5 plus 12 is 17 plus 1 is 18. So now everything is balanced. We know that we cannot leave the 2 as the denominator here because we know that you can't have a fraction. You've got to have a whole number. We can easily fix that. All we got to do is what we did before. We need to multiply by 2. All right, so it becomes, I'm just going to cross out the number rather than rewriting the whole thing. 2 times 2 is 4. This becomes 6. This becomes 10. This becomes 12. And 1/2 times 2, we just did it below, is 1. You don't really need to put the 1 there. You can if you want, but usually when you write a chemical equation, you don't put the 1 there. If you, again, recheck the tally, and you can definitely do that, you will see that, and we can recheck that real quickly. I don't want to list it totally underneath, but I'll list it here. H, N, and O. You'll see that 4 times 3 is 12. So you have 12 carbons. 4 times 5 is 20 hydrogens. 4 times 3 is 12. And 4 times 9 is 36. Then you've got 6 times 2 is 12 nitrogens. 10 times 2 is 20 hydrogens. 10 times 1 is just 10. Okay. Then 12 carbons. 12 times 2 is 24. And then you've got your O2, which is just 2, right? So 10 plus 24 is 34, plus 2 is 36. So yes, by putting those numbers in front, you have a balanced equation, and more importantly, everything is whole numbers. Again, this is a little bit more of a difficult problem, a challenging problem. Again, what I would suggest you do now at this point is pause the video or stop the video. And I'm going to go ahead and stop the video. I would go back, do these problems again on a clean sheet of paper, and check your answers. Hopefully this has been a good walk through the park on how to do balancing equations.